Margie, have you? Oh, you're muted, Margie.
There we
Have
go.
you had a chance to say hello to Michelle?
I just said hello to Michelle as I was muted. Hi, Michelle.
Hello. Nice to see you over Zoom. We talked over email, so.
Yes.
Chris, could you give me about maybe, I don't know, like 5 minutes to talk about the light pollution survey?
Right, sure.
Okay.
Yeah, we have a few other things if time permits, but we'll see what we can get to. But I'll make a note of that one, David, because that one is time limited.
A little bit, and also we've got a really good response. I just wanted to let people know that we'll probably have a separate Zoom meeting to talk about it.
Right. So if people haven't been following that discussion, we want to, we mapped Victoria in, what was it, 2010?
2010,
Looking,
yeah.
sky quality with using sky quality meters like that one. And we want to do it again because we haven't done it for 11 years. So it involves driving around the city and pointing these at the sky and seeing what sort of conditions we're getting.
Michelle, it's 10:30 where you are. Yeah.
No problem.
It shouldn't be a problem. She's an astronomer.
Are you right in, Michelle, are you right in Washington?
I used to be in Washington just near the start of the pandemic, but I moved to Boston a few months ago, so that now I can actually be on campus at MIT with coworkers and other people.
Oh, nice.
Right now, the temperature in Boston is really nice, but I think as a Vancouverite, I'm not ready for the winter time here. That's gonna hit a couple months. So my mom has actually sent me my ski jacket in the mail. It's on its way, so I'll be somewhat prepared.
Yes. Yeah, my sister has lived in Northern California for the last 20 years, and all those clothes that she had in when she was living in Calgary, some of them she's still wearing.
So we just wait a moment or two more to allow people who are connecting to connect, and then I think Margie will do the introductions for this evening.
For those who are interested in the light pollution mapping we did in 2010, I put a link in the chat.
So maybe just in the interest of time, I'll just say a few introductory remarks. So we have a guest speaker tonight, so welcome Michelle, and Margie will tell us more about that in a moment. As time permits afterwards, we have a few people who did have things they'd like to share this evening. So I've heard from Nathan, Randy, we have some Edmonton photos, and David Lee. So I don't know if anybody else had anything tonight, but again, we'll be back next week. So maybe we'll maybe just cap it there for tonight, unless it's something that's timely in the next week. But
Chris, I'll just remind people of the star party for the FDAO, but it's on the 30th, so it is 2 weeks. So
2 weeks, right?
yeah,
Okay.
so
Thank you.
we'll have more time.
Thank you for
to
the
talk about
reminder,
next
because
week.
I do try and include that when I send out my weekly announcement about.
Right.
So I'll
Yeah.
put that in the November 1st announcement. Yeah.
And it needs to be read. It's because it's the annual meeting. It needs to be, there needs to be a registration for members to link to. So
Right.
anyway, that's all.
There
for now.
is a guest speaker and.
Yes, there is. Yes. Yeah.
Thank you, Lauri. Okay, well, we have 31 people checked in, so I think if it's coming up to 25 to, and Michelle's on the Eastern time zone, so maybe we should get started. And so Margie, would you like to welcome Michelle?
I would be delighted. Dr. Michelle Kunimoto is a postdoctoral associate working on NASA's TESS mission. She leads the Quick Look Pipeline team at MIT, which is dedicated to analyzing TESS data to discover and characterize planets around the stars. As an undergrad, her discoveries of 4 planet candidates landed her on the Forbes 30 Under 30 list in 2017. Michelle is BC born and raised and received both her undergraduate Bachelor of Science in Physics and Astronomy degree and her PhD in Astronomy at the University of British Columbia. In grade 9, Michelle thought about a career as a classical violist or as an engineer. She became interested in astronomy when her dad introduced her to Star Trek, the original series, and when she acquired her great uncle's Questar telescope. Michelle will speak about how we find exoplanets, about how we identify potentially habitable planets, about what she does as a researcher with NASA's TESS mission, and about how anyone can join the hunt for new planets. Please welcome Dr. Michelle Kunimoto.
Thank you for the lovely introduction. So I'll just share my screen. And obligatory, does everything look like it's coming across okay?
Yes.
Okay, thank you. So I'm really excited to talk to you all about my research and what kinds of questions that I try to answer in my career as what I like to say is an exoplanetologist. At the end, I've left a lot of room for questions, so I really look forward to hearing them. So I want you to consider that our sun is just one star out of 400 billion stars in the Milky Way galaxy. And it could be the case that every single one of these stars you see here actually hosts a system just like our own solar system around it. We're of course familiar with our own solar system, but it could be the case that there are hundreds of billions of these in the Milky Way galaxy. So these planets that orbit other stars are known as exoplanets, where exo means outer. And they're what I'm most interested in studying. By studying exoplanets, we can better understand our own solar system, for instance, how it formed, how it evolved, and how it changed over time. In my work, there's some very key questions that I want to answer. In particular, how common are other planets around other stars? Is our sun one of the few stars capable of hosting planets, or are they common? How many planets are in your typical planetary system? What about the diversity of exoplanets? Now, just from our own solar system, we see there's a wide variety of sizes, colors, compositions, ring systems, temperatures, and so on. And all of these features can tell us really important information about how those planets formed and evolved. And of course, this is just one possible planetary system. There's a treasure trove of diversity out there that we'd still like to discover. And maybe one of the most important questions that I try to answer is whether or not there's another planet like our own Earth. And this means that it's going to be rocky and has water and could even be considered habitable. If so, how common are these other Earths? What might life look like on those other Earths? And how close is the nearest one to our own solar system? And naturally, that leads me to the last question, which is kind of a really fundamental question that I think everybody has asked themselves at some point in their life, which is, are we alone? If there's life out there, what would it look like? What kind of planet would it look like? And what kind of conditions does it need to survive? This is something that I think is both philosophically and scientifically fascinating. So first off, what do I mean by Earth-like planet? Now, there's some very basic criteria that I'm going to outline, and I just want to kind of warn you that I'm going to make a lot of Earth-centric assumptions. And this is just because Earth is our single data point in terms of a planet that can host life. So for instance, we assume that life, like on Earth, is going to need water to survive. So a planet to be considered habitable needs to have liquid water on its surface. Of course, there could very well be life out there that doesn't need water to survive, but these are the basic assumptions that we're going to use to start looking for habitable planets. So the first thing is we want to make sure that a habitable planet is small. The reason is because small planets are rocky, like our own Earth, whereas large planets are gaseous, like the gas giants of our solar system. The transition between rocky and gaseous is kind of debated. It's still unclear, but a good rule of thumb is to say anywhere from maybe 1.5 to 2 times the size of the Earth. At that point, you can consider it rocky. On the other hand, if a planet is too small, it might not be massive enough to support an atmosphere. And this is what we see with Mars in our own solar system. Mars's atmosphere is escaping because it doesn't have the gravity to contain all those molecules. So we want to make sure that our habitable planet is massive enough to support an atmosphere and protect the surface from radiation from its star. Second, we need to make sure that our planet orbits in its star's habitable zone. Now, if it's too close to its star, it's going to be too hot, and any water that would exist on the planet would boil away. Whereas if it's too far, any water would exist only in the form of ice, and it would freeze. So the habitable zone is the place where our planet orbits, and the temperature is just right. It's not too hot, not too cold, but just right for liquid water to survive on the surface. The last criteria is we're looking for planets around stars that are similar to our sun. The reason is we believe life needs billions of years to develop on its planet. So that means that its star is going to have to live at least that long. We don't want it to go supernova before life has a chance to develop. So this is one of the reasons why big and hot stars, much hotter than our own sun, are not good candidates for looking for habitable planets. These ones don't live very long on astronomical timescales. Not very long means less than 1 billion years. But really that's not long enough for life to be able to develop on its planet. On the other end, stars that are smaller and cooler than our sun live a lot longer. So they're really good places to look for habitable planets because they're going to provide a stable environment. One other good thing about these is that they're also very common. So these small red dwarfs are about 70% of all stars in the Milky Way galaxy, which means they could actually support most of the potentially habitable planets that are in our galaxy. One caveat is that these stars are so cool and small that their habitable zone is really close to the star. It's much closer than our own Earth orbits the sun. That means that the planet is going to be bombarded by a lot more radiation than what we're used to. Now, again, that doesn't mean that life won't be able to exist and adapt to that extra radiation, but astrobiologists try to answer questions like, what would life look like if it was faced with those kinds of harsh environments? Is it possible for life to be able to exist? And of course, sun-like stars are going to be your ideal places to look for potentially habitable planets because we at least know that Earth exists. We're here on planet Earth and we're orbiting a star just like our sun. So now we know how to classify potentially habitable planets. How do we go about finding them? Well, to place exoplanet hunting in context with planet hunting in general, I want to dive back a few thousands of years to our ancient ancestors. So the first planets that humans knew about were Mercury, Venus, Mars, Jupiter, Saturn, and of course our Earth. And the reason is because these are all visible with the naked eye. If it's a dark enough sky and there isn't light pollution, you'd be able to see any of these depending on the time of year. In fact, the earliest measurements of these planets go back to about 5,000 years ago by the ancient Mesopotamians. And these observations are one of the reasons why astronomy and planetary science is considered one of, if not the oldest sciences. It wasn't until a few hundred years ago, compared to a few thousand years ago, that the next planet in the solar system was discovered. In fact, William Herschel, who discovered Uranus, was not looking for a planet at all. He was doing a survey of nearby faint stars, and Uranus just happened to cross his telescope view. So this was actually the first planet to be discovered by a telescope. Now, there were some strange perturbations in Uranus's orbit that indicated another body was orbiting beyond the orbit of Uranus and gravitationally interacting with it, tugging on it as it orbited. And people were able to predict based off these perturbations that there must be an 8th planet of the solar system. And that ended up being Neptune, which was discovered less than 200 years ago. Now, there were still some perturbations in Uranus's orbit that were detected even after the detection of Neptune, and this turned out to be Pluto. So for several decades, people kind of saw these perturbations in Uranus's orbit and were driven to discover what was known as Planet X, X meaning unknown, not the Roman numeral for the number 10, but just X as in the unknown. And it was finally discovered in 1930 by an American astronomer, Clyde Tombaugh. So what he did was he used what's known as a blink comparator to rapidly switch between 2 images of the night sky taken at 2 different times. And he would essentially play a spot the difference game. Because stars are going to be so far in the background, they're not going to move a whole lot between observations, whereas Pluto, or this mysterious planet X, is going to be so much closer, so you should be able to see it's the single dot that's different between these 2 images. Now, for those of you that are still looking for it, that tiny dot there is Pluto passing in front of the telescope's field of view. Now, I should mention that throughout these last centuries of history I've zoomed through, there have been a lot of objects that were initially classified as planets, but later they lost their planetary label. For example, the dwarf planet Ceres is the largest object in the asteroid belt. It was discovered in 1801, and when it was discovered, people classified it as a planet in the solar system. But over the next 50 years or so, more and more of these small objects started to be discovered in the asteroid belt, and people realized that they deserved their own classification. So they were later classified as asteroids. And of course, we know that the same fate would eventually befall Pluto. But regardless, at this point, what I've rounded up is the 20th century view of planets and the solar system. This is the number of planets that most people alive today, including myself, learned were the 9 planets of the solar system. And these were also all the planets that we knew about in the Milky Way galaxy. Starting in around the 1950s was the first proposed detections of planets around other stars. But unfortunately, all of them turned out to be data flukes, and quite simply, the technology just wasn't there yet to be able to find planets around other stars. These are going to be so much farther away than the solar system planets that you can't, use a backyard telescope to be able to find them. So astronomers had to get quite creative in coming up with ways to find exoplanets. Now, of course, I wasn't around in these early days of exoplanet detections, but I've talked to some people who were, and they expressed to me a feeling that exoplanet hunting was a totally taboo topic. In fact, they would give a talk and people would get up and leave the talk because they just said, this is a waste of time. You're not going to be able to find a planet around another star. I mean, it took us thousands of years to find Uranus and Neptune. People just didn't believe that it was possible. And all of those naysayers were proven wrong just about 30 years ago when the first exoplanet detections were made. So this was made by Alex Wilson and Dale Frail. They discovered 2 planets orbiting a pulsar. So it kind of makes me sit back in awe that the oldest science, this age-old history of studying planets in our solar system, and exoplanet hunting is one of the newest sciences. They both, they have this wonderful connection here. So what Wilson and Frail did was they used what's known as the pulsar timing method. So a pulsar is a pulsating radio star, and it rapidly rotates and emits radio waves along its poles. So think of it like a lighthouse beacon as it's spinning around. Every time the Earth is facing that pulsar emission, we'd be able to detect those emissions. Now, pulsars are so accurate in how quickly they rotate, which is typically a few milliseconds or a few seconds, that they're considered the most accurate clocks in the universe. But let's say we throw a planet into the mix. So now what's going to happen is that planet is going to interact gravitationally and cause that planet and the star to orbit around a common center of mass. So we'll see basically the star will wobble slightly as it orbits. Now what happens is those pulsar emissions at some points in the star's orbit, they'll have to take a little bit longer to reach our Earth because they have longer to travel. So the emissions will arrive slightly late than what you'd expect. At other times in the star's orbit, it'll be a bit closer to the Earth, so those emissions will arrive slightly early. So if you were to track the amount of time that it took between each emission, you'd be able to see those that are slightly early, those that are slightly late. That tells you that there's a body that's in orbit around that pulsar and affecting it gravitationally. So as I mentioned, pulsars are so accurate that you're actually able to detect a body that's as small as 1/10 of the mass of the Earth in orbit around one of these pulsars. Now, I do want to mention there were actually a couple of exoplanet discoveries that preceded the pulsar planets that are a bit lesser known. For various reasons, they weren't able to be confirmed right away, which is why they're not considered the first exoplanet discoveries, but I still wanted to highlight them. In particular, the first one was actually made by a team of Canadian astronomers, Bruce Campbell, Gordon Walker, and Stevenson Yang, who were based at your very own University of Victoria, as well as my alma mater, University of BC. So these observations were at the very limits of instrumental capabilities at the time. So their discovery wasn't confirmed until 2002, but their paper announcing this discovery was out in 1988. So there is an argument that the earliest advancements in the exoplanet field actually happened right there in Victoria, BC. So one of the things that they pioneered was actually the second most successful exoplanet detection method to date, which is known as the radial velocity method. So as we've already covered, a planet orbiting a star will cause it to wobble slightly around its center of mass. But if it's not a pulsar, we don't have those pulsar emissions to time whether it's far from our Earth or slightly closer. Instead, we can use a technique known as Doppler spectroscopy. So every star has a unique fingerprint in its spectrum. These are basically spectral lines, absorption lines that tell you information about the chemical composition of the star. And when the star is moving towards you, that light is going to be slightly blue shifted, so shifted towards the blue end of the spectrum. And as the star moves away from you, it'll be shifted slightly to the red end of the spectrum. As a result, you'll be able to tell how quickly that star is moving based off of how much its star spectral lines are shifting. And that way you can tell that that star must be in orbit around some common center of mass and is having some other object interact with it gravitationally. Now, these frequency shifts are kind of like if you're standing on a sidewalk and an ambulance is going by, and you know how the sound of that siren changes as it moves by you, as it's moving towards you and as it moves away. That's the Doppler shift. And this is exactly what's going on, but instead of with sound waves, it's with light waves. So this method is actually capable of detecting a change in a star's movement of only 1 meter per second. I just want you to consider that, these are stars that are tens, hundreds, thousands of light years away. And depending on how bright it is, we can detect a change in its movement of only 1 meter per second. Unfortunately, that's not quite enough if we want to find potentially habitable Earth-like planets around sun-like stars in year-long orbits, because these planets are so far from their stars and they're so small, they don't have a lot of mass, that they only affect their star on the order of about 10 centimeters per second. So the RV method isn't quite there yet to be able to find these. However, in the next generation, or the next era of radial velocity instruments, we are actually going to be able to do this for the first time. So there's a lot of other detection methods, and I'm happy to describe any of them if you have other questions about these at the end. I won't have time to go through each one, but I do want to highlight the one that I use in my work, which is known as the transit method. So the transit method has the basic idea that a planet will pass in front of its star as it orbits, and then it's going to block that star's light. What you can do is, if you've got a telescope trained on that star, you can measure its brightness over time, and every time the planet transits or passes in front of its star, you'll see a temporary decrease in the brightness of that star. The depth of these transits gives you an estimate of the planet's size, because a large planet is going to block a lot of light and a very small planet will block very little light. The time between each of these transits also tells you how often it takes for that planet to orbit. So if there's a full year between transits, that means it has an orbital period of a year, just like our own Earth. And one of the downsides of the transit method is that a planet needs to pass directly between you, the observer, and the star itself. And there aren't very many orbital inclinations that allow this to happen. So basically, even if the orbital plane is slightly inclined, that planet will never transit, it will never block the star's light. You won't see any change in the star's brightness because of this object. Just for example, if we want to detect an Earth-sized planet transiting a sun-like star in a year-long orbit, the probability that the orbital inclination is just so aligned is less than 0.5%. So very rare events. An additional downside of the transit method is that there are very common signals that can mimic a planet. Of course, a planet isn't the only thing that can block a star's light and cause a transit. It could be a low mass star. It could be just another eclipsing binary star that's passing in front of your star and block its light. So we do have to be careful once we've found a planet that there's some telltale signs that we can use to make sure that what we found is indeed a planet. Anyways, all of the various detection methods in these first couple decades of exoplanet detections, well, there was really this explosion of detections since those first ones in the early 90s. There were a few dozen exoplanets found by the turn of the millennium, and by about 2010, so just 10 years ago, there were a few hundreds of exoplanets that were found. Now, this is a snapshot of exoplanet detections as a function of planet mass on the y-axis and orbital period on the x-axis. And as you can see, the vast majority of planets are larger than Neptune. A lot of these early detections were also consisting of hot Jupiters. So as you can see, there's this clump here of very massive planets at very small orbital periods. So these are totally unlike anything we see in our own solar system, where all the small planets orbit close to the sun and the large planets orbit really far. So the fact that these existed, which we didn't think was possible, caused theorists to have to completely rewrite their planet formation and evolution theories. But you'll notice that what was missing from these detections was there was no small planets like our Earth that were being discovered. They were 85% larger than Neptune. And the reason for this is not that they're not in existence, it's just that technology wasn't there yet to be able to find these, because they either have very small radii, so you're not able to see them with the transit method, or they have very small masses, so you can't find them with the radial velocity method. However, all of that changed with the Kepler mission. So this was NASA's first exoplanet finding mission, and it was really the first mission capable of finding small Earth-sized planets around sun-like stars. And specifically, it was designed to try to find planets in the habitable zone like our own Earth. So Kepler used the transit method to find exoplanets. And as you can see here, our Earth is really tiny compared to the sun. So it needed to be able to find a change in a star's brightness of only 0.008% if it wanted to find an Earth-sized planet transiting its sun-like star. Now, to give you an idea of what this means and how difficult it is, I want you to imagine the Empire State Building, and all the lights are on, it's the nighttime, all the window shades are up. Somebody closes a single window by just a few inches, and there's, I think, about 6,500 windows to the Empire State Building, and you would need to detect that change of brightness from that action from over 100 kilometers away. Now consider that a transit will only last a few hours at a time, and if you're looking for another Earth, it will only happen once a year. So you need to stare at that star continuously for years if you just want a chance at seeing even a single transit. And that's essentially what Kepler did. So Kepler observed 200,000 stars continuously for a period of 4 years. Now, as you recall, the transit probability is really low, less than 0.5% chance that a planet will actually transit its star. And we had no idea if Earth-like planets were common or rare. So Kepler had to observe a really large number of stars to be able to find even a small number of planets. So Kepler had a field of view of about 115 degrees squared. That's about the size of the sky if you were to hold your arm your hand at arm's length, the area of the sky covered by your hand is about 115 degrees squared. So for a telescope, that's actually really big. It was at the time the largest mirror ever sent into space at about 1.2 meters in diameter, and it was also the largest camera system sent into space. So Kepler stared at the same section of the sky in the Cygnus Lyrae constellation for that full 4 years. It was launched into an Earth-trailing orbit in March of 2009. And as you can see here, it's got those blue solar panels that are always pointed towards the sun so that it has power. In order for it to point at the same section of the sky for the entire orbit and have its solar panels pointed at the sun, it would rotate on its axis 90 degrees 4 times a year. Now, just to give you a sense of how successful Kepler was and how revolutionary it was, this is a plot of planet detections per year. The blue are non-Kepler detections and the red are Kepler detections. So those are all just from Kepler alone. And these were just the early years of the mission. It launched in 2009 and it didn't finish, several years of observations until several years later. And in 2014, they released their first major catalog. And it just kind of blew everybody else out of the water. So just another view of how successful Kepler was. This is that plot I showed you earlier of pre-Kepler detections. So those before the year 2009 and 2010. And this is what it looked like after the Kepler mission. So we really were finally able to fill in that small exoplanet parameter space, and it just totally revolutionized how we saw the average planet in the galaxy. So by the end of its 4-year mission, Kepler found 2,400 confirmed exoplanets, which is more than half of all confirmed exoplanets that we know of today. And it's also found about 2,400 candidate planets that very well might still be planets, they just haven't been confirmed yet. Now, unfortunately, Kepler did suffer instrumental failure at the 4-year mark. It could have gone for longer, but it needed 2 of its 4 reaction wheels working, 3 of its 4 reaction wheels working so that it could maintain pointing stability at the same section of the sky. So once a second one failed, it was no longer able to maintain that pointing, and that official mission had to end. However, the rest of the telescope was still in perfect working condition. And as a result, it was actually reborn as the K2 mission. So Kepler engineers, what they did was they actually figured out that radiation pressure from our sun could push on the telescope and act as a 3rd reaction wheel to balance it out and have it be able to point at a section of the sky until it had to rotate again. So K2 observations were able to span 90 days at a time, of course, instead of the full 4 years. And basically wherever Kepler happened to be pointing, in order to make use of radiation pressure from the sun, it would be able to point at that section of the sky. So K2 was able to find several hundreds of new planets. Of course, all missions have to come to an end, and in 2018 was the final year of Kepler. So Kepler ran out of fuel and officially shut down. Somewhat poetically, the date that Kepler shut down in November 2018 was actually exactly 388 years and 1 day off of the anniversary of Johannes Kepler's death. So now that we're at the present day, TESS is NASA's current exoplanet finding mission and the official follow-up to Kepler. Now, unlike Kepler, which looked at 200,000 stars in the same section of the sky for a long period of time, TESS is actually looking at all nearby bright stars for exoplanets. What that means is we're looking at tens of millions of stars to look for signs of exoplanet transits. So the way TESS works is it has an enormous field of view. It has 4 cameras that stare at a strip of the sky here, known as sectors, for 27 days at a time. And after that 27 days, it rotates to look at the next strip of sky. 13 sectors later, it's looked at in the entire year of observations, and it's basically covered an entire hemisphere of the sky. So this was the pointing scenario of our primary mission. The first year it looked at the southern hemisphere, and the second year it looked at the northern hemisphere. Right now we're going into our 4th year of operations, and we're going to be we've re-observed a lot of these sectors. We're also looking at new sections of the sky. So hopefully we have coverage of the entire night sky. One thing you'll notice is that these cameras down here, there's no overlap between sectors. So these stars are only observed for 27 days in a given year. But as you work closer to the ecliptic poles, more and more sectors are overlapping, which means that stars up here are observed for a full year before TESS switches to the next hemisphere. So basically, TESS is able to observe stars anywhere from 27 days to a full year. And as the TESS mission continues, we'll be getting more and more overlap and longer baselines of observations. So the team I lead at MIT makes light curves for about 1 million stars every month, which is about the number that are observed brighter than some magnitude. So we take the pictures that TESS takes of the night sky and we convert those into measurements of brightness over time, which are known as light curves. And then we run our planet search pipeline on these to automatically search through these light curves and try to find signals in the data that are caused by planets. So in this case, our pipeline would have picked up these two transits here. You can see that they have a similar depth, and the time in between them gives the orbital period of the potential planet. The next thing we do is we take a look at these signals and ask ourselves, is this a planet or not? As I mentioned before, there are examples of false positives. So we have to be careful that this is indeed a real planet transit. It could be a systematic, it could be an eclipsing binary, it could be a whole lot of other things. And we run several tests on them just to make sure. And actually the last test we do is with our own eyes. So we're trained to recognize what a planet transit looks like. It typically has a very nice U shape, so kind of this flat bottom here. Binary stars tend to have these very V-shaped transits. So groups of vetters basically will sit down at the end of every month and we'll look at hundreds of these signals and identify manually which of these we believe should be pushed to planet candidate status. And those become TESS objects of interest. Now, I want to mention one of the projects that I'm leading actually was able to discover about 1,600 planets, contributing 1,600 new TOIs. This was specifically a search of fainter stars, which is why they're going to be larger planets, because around fainter stars, the light curve precision is much noisier, so we're really only sensitive to large planets. But it's work that I'm really proud of, and I'm continuing to add hundreds of new planets every few months with this project. Overall, TESS has been able to find 152 confirmed planets and over 3,000 candidate planets, of which 1,600 are from that project that I just mentioned. And I've been running simulations of predicting the TESS yield over the next few years, because this current extended mission is going to be 1 year longer, but we'll have a second extended mission, hopefully for another 3 years. And based off my predictions, TESS will be able to find more than 10,000 bona fide exoplanets. And thankfully, that's not where we have to end. Unless there's a terrible case of instrumental failure, TESS will be able to continue observing the night sky and continuing to get more and more overlap of different targets. So now that we've got to the present day, as of this morning, there have been 4,500 confirmed exoplanets discovered. A huge chunk of those, of course, are going to be discovered with the transit method. And just as a reminder, these are just confirmed planets. There are still 5,000 planets, planet candidates between Kepler and TESS that can still be confirmed in the future. A whole lot more than the 0 that we knew about just 30 years ago. Now, based off of all confirmed exoplanets so far, we can estimate that around every star, they host at least a single planet, probably multiple planets. So that means that there are hundreds of billions of planets in our Milky Way galaxy. And of course, as technology continues to improve, we'll be able to push these detection limits. So even the transit method for small planets is reaching its limit. We're not able to find the smallest planets and those at the longest orbital periods because they require so many observations. So the more missions come out, the longer the observations get, we'll be able to push on that detection limit and find even more planets. So the planets we found so far are incredibly diverse. I mentioned already the hot Jupiters, which were kind of those earliest really exotic cases that were unlike anything in our own solar system. But there have also been planets found around not just one, but multiple stars, like in Tatooine in the Star Wars movies. We lovingly refer to these as Tatooine systems. There's also planets that are so dark, they're colored basically just the darkest black paint, and they absorb so much heat and radiation. And there's even some planets that we believe are made entirely of diamonds based off of the conditions that they're in around their stars. And of course, this is just a small sampling of the kinds of diversity of planets out there. There's, I'm sure, stuff that we can't even imagine yet. One of the most exciting planetary systems I think that has been discovered so far is the TRAPPIST-1 system. So TRAPPIST-1 is a star that's really, really small. So if you were to shrink down that orbit so that it's actually how it is compared to our solar system, though all 7 of those planets would be able to fit within the orbit of Mercury. And another cool thing about the system is that 3 of its planets are actually in the habitable zone. So as I mentioned, the habitable zone means that it can potentially has the right temperature for liquid water to survive. And because the star is so small and so cool, that habitable zone is really, really close in. So 3 planets of it, 3 planets in the system are all in the habitable zone, and all of them are roughly Earth size. So this is going to be a fascinating system to study in the future. In terms of planets and like the Earth in general, so far there have been about 20 confirmed exoplanets that are both in the habitable zone and are roughly Earth size and are around those kind of stars that are similar to our sun and smaller. So all of these are going to be really fascinating targets for more observations in the future, so we could better understand how habitable they are and what it means for another planet to be habitable. Based off the number of planets we found with Kepler, we can estimate that potentially about half of all sun-like stars in the Milky Way galaxy actually host a small planet in its habitable zone. That means there could be hundreds of billions of potentially habitable Earth-like planets in the Milky Way galaxy. Of all these planets, the one that's most similar to Earth so far is Kepler 452b. So this orbits a star that's very similar to our sun. It's got the same spectral type. It's only a little bit larger than the sun. The planet orbits on a period of 385 days, which is only a little bit longer than Earth's own orbit. And it's only 1.1 times the size of the Earth. So it truly is, I think, Earth 2.0 so far. Obviously, we don't know if it's actually habitable, but you know, I'm sure that there's so many more like it that we can find. I think if you were to ask me what my favorite exoplanet is, it would actually be the one that's around Proxima Centauri. So Proxima Centauri is the closest star to our own sun, and it hosts a potentially habitable Earth-sized planet in its habitable zone. So it just amazes me that these have to be common, right? If the closest star to our sun has a habitable zone small planet, they've got to be super common. So what would be next? After we find a planet that's in the habitable zone, how can we find out more about it and actually ask ourselves whether it is capable of supporting life? Now, of course, we haven't discovered life on another planet, but finding life on another planet is a very long investigation path, and we are just starting to take the first steps. So one of the first things that we can start doing, which is what we can do now, is look at planets with multiple detection methods. In particular, the radial velocity method depends on finding the gravitational influence of a planet around its star. And from that, we can estimate the mass of the planet that has to be causing that star to wobble. Meanwhile, the transit method gives us the radius of the planet, and the combination of these two gives us the density of the planet. And that places really important constraints on the planet's composition. So based off the planet's density, we can see how similar that density is to our own Earth. And that can tell us if its composition is Earth-like, rocky, iron-rich, if it's a water world, if it's mostly gaseous. And that will start to tell us a bit about what the surface of that planet would be like and what conditions the planet has. We can also characterize the atmosphere of other planets. So this is a technique known as transmission spectroscopy. The idea is that the transit method you can see that the planet transiting its star is obviously going to block that star's light because rock is opaque. You can't have light pass through it, but you can have light pass through the planet's atmosphere. And as we know from greenhouse gases, for instance, different molecules in our atmosphere scatter light, absorb light, emit light differently in different wavelengths. So if we were to observe a planet transit and observe how that transit changes as a function of wavelength, we can tell what molecules are in that planet's atmosphere and causing it to appear more opaque in some wavelengths than others. So this is how we'd be able to tell, for instance, if a planet has particular biosignature gases in its atmosphere, like water, oxygen, methane, and carbon dioxide. So far, unfortunately, this technique is only capable of characterizing large planet atmospheres, so planets that are hot Jupiters. It doesn't quite have the, we don't quite have the technology to do this for the smallest exoplanets. However, the upcoming James Webb Space Telescope, if it really does launch, and I really, really hope it does, it's going to be able to look at the TRAPPIST system and characterize the atmospheres of those planets. So this would be a fascinating topic to follow up on in the next few years. And one thing I also want to keep people in the know about is that in a few months is going to be the results of the 2020 Decadal Survey. So this is a census that happens once every 10 years. And basically the whole astronomy community comes together and decides which next major telescope should deserve funding. And one of the final contenders is HabEx, the Habitable Exoplanet Observatory. So this is, of course, just a concept now. If it gets accepted, it won't launch until 2035 about. But the concept is to directly image exoplanets that are Earth-like in year-long orbits around sun-like stars. So unlike the transit method and the radial velocity method, which are indirect methods of finding planets, this will be a direct image of habitable planets. So I'm really crossing my fingers that it's selected. We'll find out in a few months, based the results of the census, and this mission is also going to be able to characterize planet atmospheres. So before I finish up here, I do want to talk about a few avenues that anybody can get involved through for looking for exoplanets, whether you're a high school student, an undergraduate student, or an amateur astronomer. The first is to recognize that Kepler data and TESS data is all available to the public on the Mikulski Archive for Space Telescopes. Anybody, as long as they have an internet connection and a large enough hard drive, can download all of Kepler's data if they'd like to. And there are numerous online resources for finding and analyzing transit signals. In fact, the general exoplanet community has really strongly shifted towards community involvement. So there are a lot of people who like people, being able to contribute and make independent detections. So this is actually the route that I did for my undergraduate degree. I just did a summer research project, and my task was to download some Kepler data. I just looked at 400 stars and tried to see if there were any planets that might have been missed by previous searches. And as a result, I was able to find 4 new planet candidates in this data. So I had no programming experience at this point. This was also my very first research position as an undergrad. So if I can do it, this is very possible for you as well. I also want to mention that Kepler was just 200,000 stars, and TESS is looking at tens of millions of stars every year. And we don't have the resources to look at every single star. I have no doubt that there are planets that are just waiting to be found. And all of TESS data is available to the public after about 2 months after it's actually observed in the sky. So it's available to the public really quickly. And we actually get submissions from exoplanet community members basically on a regular basis. Every month, people submit planets that they found that we didn't find, and we add those to our TESS Object of Interest catalog. So these are the 4 planets that I found as an undergrad, just to kind of highlight. There was quite a wide wide diversity of these. A lot of these tended to be the really difficult to find signals, which would make sense why they were missed by previous searches. Now, if you don't want to include any programming experience or data analysis, beyond using your own eyes. There's also a really wonderful website called Planet Hunters TESS. So this is a citizen science initiative. They host a website where you can view and interact with TESS data to search for planets via manual inspection. So again, none of this involves any coding experience, but rather it depends on the human ability to pick out patterns in the data. In particular, humans have a remarkable ability for pattern recognition, and we can see what computer algorithms miss. Citizen scientists have actually discovered some of the most interesting and puzzling light curves that wouldn't show up in regular transit searches because those are designed to find just transits. And they've already found hundreds of planets. And again, these are people who are logging into this website, looking at planet transits in their browser and identifying really incredible systems. If you were to find something interesting, you would of course get credit for your discovery and be able to participate in published research. And one last thing is anybody can actually join the TESS vetting team. So all of those hundreds of signals that my team outputs, we then pass those off to group vetters to look at them, discuss them in groups, take a look at them and see whether they agree or not that these should be considered planet candidates. And anybody can join that team. We've got vetting sessions where you can be trained as a vetter so that you can learn about different false positives and what it looks like. And it's a really interactive way to interact with the rest of the exoplanet community, and people from all around the world join these vetting sessions. So if you're interested in looking at some real planet candidates before they're even released and helping identify new planets and test data, please ask me any questions about this. So what have we learned? The first thing is that exoplanet hunting has really exploded in the last few decades, and it also shows no signs of stopping. Again, the first exoplanet detections were less than 30 years ago, and today we know of thousands and thousands. And there are thousands more candidates just waiting to be discovered. There are also several space-based missions that are going to be launching by the end of the decade that are all going to be contributing to the search for exoplanets. In particular, the Plato mission is from the European Space Agency, and it will be using the transit method to find potentially habitable planets around sun-like stars and cooler. And you can see that's a very popular trend. There's also the Nancy Roman telescope, which is mostly going to be focused on cosmology, but is also going to have some exoplanet applications. And in particular, it's going to be expected to find the small planets that were out of the reach of Kepler. So those are going to be ones that are on orbits, potentially even thousands of days. We've also found that planet detections have totally changed how we see the average planet. We've gone from thinking that the average planet was larger than Neptune to smaller than Neptune. We've also found examples of so many of these exotic planets like hot Jupiters and Tatooine planets and diamond planets. And all of these totally influence and cause the rewriting of planet formation and evolution theories. One of the most intriguing questions for me is the most common size of planets so far are those that are between the sizes of the Earth and Neptune, yet our solar system doesn't have a planet like this. So our solar system, why is that? That's a question that has struggled, that theorists have struggled with, because they want their formation theories to form these planets, but our solar system doesn't have an example like this. So that's something that people are going to have to think about. And of course, we've also found dozens of planets in the habitable zone and hundreds more if you include candidates, including one around the nearest star to our sun. This, of course, has exciting implications for the search for life in the galaxy. And what's incredible is that all of these detections have turned what used to be purely in the realm of science fiction into a fast-growing and well-established subfield of astronomy that I'm really excited to be a part of. And all of these kinds of exoplanet discoveries are those that can be made by really anybody. High school students have discovered planets. I, as an undergrad, was able to contribute and make some interesting discoveries. And members of the amateur and professional astronomical communities are always contributing new planets to the data sets. So anybody can join in the hunt, and that's one of the reasons that I love what I do. So thank you.
Well, thank you very much. I guess we can take some questions, and maybe it might be best if there turned out to be a lot of questions to use the hand raising in the reactions area. But did I see, Dave, did you have a question? Because I see you're unmuted.
No, I was just reading after it all.
Okay, Lauri, would you like to ask your question?
Yes. Hi, Michelle. That's great.
Hi.
Thank you. What about rogue planets? Ones that seem to not actually go around a sun or a star kind of at all? Or is that something kind of out there that's not real?
It is real. We've detected those. So this is actually something that I find kind of funny because the International Astronomical Union has changed their definition of planet several times. That's one of the reasons why Pluto is no longer considered a planet. And their kind of official stance is that it does have to orbit around another star. Yet we found these planetary mass objects that we call rogue planets that don't orbit a star at all. And I could describe how we were able to find them. It's using a technique that I didn't talk about today, but we definitely have found several examples of these. What we believe is the origin of these is they were initially part of a stellar system, so they would have formed around a star, but then some event might have happened, like the two stars interact with each other and the whole system was just thrown out of whack. So that rogue planet was originally part of a solar system, and it would have just been thrown out of its orbit and now is found just kind of freely floating around in the galaxy.
Okay, thank you.
David?
Thank you, Michelle. What a wonderful talk. I had a question for you regarding the role of citizen science. You mentioned a couple of avenues to participate. Does an amateur have to start from scratch, or do you have like candidate lists that we could work from?
Do you mean in terms of learning how to identify transits, or?
Well, I think if we want to aid in finding these or looking at transits, would you have things that are ready to go? Like I'm just thinking about some of the things that are on the AAVSO where they have sort of like candidate lists to check out or check.
So this is kind of the interface that you'd be met with. It would tell you whether the data has already been looked at by other people. It'll say, this workflow is finished. You can still look through the system, and there's a system where you can leave comments next to any system. So even if it's already been looked at, you can contribute your thoughts, join in the discussion with other people who are adding in their thoughts around the world. And it would tell you if it was actually new data that hadn't been looked at, hadn't been scoured through by citizen scientists. There's also planet catalog lists, so you can always see which stars already have planets found around them. The NASA Exoplanet Archive in particular is kind of the central resource for those kinds of catalogs, whether you're thinking of Kepler data or TESS data or anything from any other missions. And those kinds of questions also, the people who run the citizen science planet hunters, they're constantly compiling the data from users and helping write papers to really publicize the discoveries from citizen scientists. So they would be great resources to talk to as well.
That's wonderful. Thank you.
Randy.
Hi, that really was an inspiring talk. Thank you. I'm wondering, how can your example of the Empire State Building blows me away. How little a difference you're looking at, and knowing that the sun is very variable. It's not going to be a dead flat curve. And one of the things
like this
is are the sunspots.
Yeah.
And how can you see a difference between I guess it would be a 10-day sort of period when that sunspot goes around. But how do you know that it's not just a really close planet?
Yeah, so this is a really good question, and one of the reasons why the vetting team is so important in our process. So there are definitely telltale signs that we have for looking for exoplanets. One of the things I mentioned was this kind of consistent U-shaped dip. So we really want to make sure that it looks like a U. It has a kind of a flat bottom here. The left side and the right side of the transit are symmetrical. And what we're really keying in on is these kinds of events, but repeating. So we really want to see at minimum 2, of course, to be able to confirm a period. But at, a lot of these transits will happen dozens of times. So if it's the same event, the same symmetric event with the same depth every time, the same duration every time, that just gives you more and more confidence that it's not something like sunspots, which often have quite variable shapes and can be quasi-periodical. So this is an example of intrinsic stellar variability that isn't caused by a planet passing in front of the star or a planet passing in front of the star, but just natural variability within the star. And as you can see, it has these shapes that are inconsistent with a planet transit. So there's a lot of groups that have been trying to write automated vetting pipelines to do this so that it removes the need for humans to have to take a look at these. I'm part of a group that's trying to do that with machine learning. But our eyes are really good at spotting the differences and the subtleties in what makes a transit shape a transit.
So as a supplemental, is the noise that you're showing us here, is that noise, or are those little variations like sunspots? Are those stellar variations?
These are stellar
signal?
variations. Yeah, so one of the things that we do, I'll just bring this back to this picture. So this is a TESS star, and as you can see, there's all these dips, and it's going up and down throughout. And some of these might even happen to land at the same consistent time, like a sunspot that's periodic. So one of the things that we do is we detrend the light curve. So we try to flatten it out as much as possible. And we know that planet transits should happen, over, X number of hours if we're looking for a planet transit with X orbital period. So any kinds of variability that aren't consistent with that planet transit, we just detrend out. So that's one of the ways we can get rid of intrinsic stellar variability and are just left with the shorter duration planet transits instead of the variability.
So cool.
Les.
Yes, Michelle, I hesitate to take us away from the exciting topics that you're most interested in, but I had a kind of a query about something from 20 years ago, the Canadian Hubble Telescope, also called MOST. And yeah. I remember a talk by Jamie Matthews where he touted the possibility of discovering exoplanets, but I never followed up with anyone to understand how many planets may have been discovered using MOST. Do you have knowledge of that?
Ooh, I don't actually know the number of discovered planets. MOST definitely did discover some new planets. I think one of the landmarks was 55 Cancri E. Actually, Jason Rowe is a former Kepler team member. He did his postdoc with Kepler and found a ton of planets with Kepler, and he was Jamie's previous PhD student. And Jason's PhD work was actually on getting the first albedo measurement for a planet, and that was done with MOST. So that was kind of a landmark. So albedo is the reflectivity of a planet. A high albedo means it's very absorptive. An albedo of 0 means that it's like a mirror. It just reflects all light. So MOST actually kind of pioneered getting albedo measurements for exoplanet transits. But in terms of the number of planets discovered, definitely, more than 0, but I don't know the actual number.
Thank you.
Are there any more questions? Peter.
Hi, Michelle. Thanks very much for your talk. And one of the points that you made that I find really interesting, you've obviously made the effort to talk to these guys from the late 80s, Gordon Walker and his team, who had some early observations. I've often wondered why they didn't pursue it. Why didn't they stick to their guns? Do you know why they because they could have hung in there and insisted that their observations were correct. And 10 years later, they would have been the Nobel Prize winners. Yeah.
Well, I guess that's what peer review is. It needs to be more than just your team to sign off on it. The peer reviewers would have just felt, especially because these would have been B first detections, it really had to be confirmed and solid. So they must have just felt that there wasn't enough data to be able to confirm the period of the planet, etc. So I know that would have been amazing. I have talked to Gordon Walker, and he's just about the most humble and sweet person you could talk to. And so he shared a lot about what it was like being an exoplanet hunter in those early days, and kind of being faced with a lot of obstacles, I guess, getting people to take the work seriously because it was so new and people just didn't think that it was possible. So there is some of that. I do wonder, like, if it had come out now, it may not have had to wait so long for confirmation, but I think just because it would have been the first, it not quite enough for the peer reviewers to be confident.
We have one question in the chat. So the telescope in your project, is it true that it's orbiting the moon? And if so, was there a reason for that?
It's not orbiting the moon. I guess I don't have an image of where it's orbiting. So let's see. So it is in orbit around the Earth, and basically it has quite an elliptic orbit. So it will take the observations, and once it spins around and it's really close to the Earth, that's when we download the data. So that was the reason for it kind of keeping in this orbit and staying close by, but it's not an orbit around the moon.
Okay, thank you. Are there any other questions for Michelle?
Sure, I have one. Well, go ahead.
You go ahead first, Dave.
I was just wondering, I don't know how involved in that part of the research you are, but I was wondering if you saw an atmosphere with a lot of molecular oxygen in it. Would that be a pretty surefire indication of life? Just given that the Earth's oxygen was all organic.
Yeah, so that's a question for the astrobiologists. I can't really speak for them because this is a little bit out of my comfort zone, but oxygen itself wouldn't be enough. So what they typically look for is specific combinations of biosignature gases. So it can't just be oxygen, it also has to be oxygen and carbon dioxide and water, all those biosignature gases, is some kind of specific combination. Now, this is going to be, I think, really exciting, but also very difficult science to do. I mean, we've seen over the last decade with methane discovered on Mars and phosphine in the atmosphere of Venus, like these kinds of biosignature detections, even in our own solar system, are those that are heavily debated and heavily, I guess, not just peer reviewed, but just they're under so much scrutiny. So there's still we only have the Earth to go off of. There's still so many unknowns that we can't say for sure that a single, biosignature gas means that there's life. But that's one of the things that astrobiologists are trying to do, is understand what combination and what abundance of biosignature gases could indicate life, because it wouldn't be able to be produced by a abiotic process or chemical equation.
Thanks. Great talk. That was really interesting.
Nathan, did you have a question?
Oh yeah. Well, I'm pretty sure that this isn't an issue, but I'm just wondering, are the planet candidate data lists designed to rule out Earth?
Yes. So this is one of the reasons why those early 1950s exoplanet detections were all data flukes, is they kept detecting the Earth because they didn't take into account that, we're not stationary on this planet. It's spinning around as well. So there's going to be changes in star positions because of Earth's movement. And, you know, there was actually a published paper that came out. I don't remember the title or what year it was, but it was in the mid 1900s. And it did say, like, we found a planet with a period of 365 days. This is incredible. And they had to release a second paper saying, sorry, it was Earth. So we're, you know, at this point, we have a ton of fail safes in place. You know, we can make those corrections for the Earth's interference. The transit method, it's not as needed just because we're looking at the changes of another star's brightness. And but there's definitely some other detection methods that are really sensitive to the Earth's movement, and we do make sure to take those into account.
Thank you. That was a great talk.
Thanks.
Any final comments or questions? I think Margie, you were going to say something too.
Yes, Michelle, in interviews I have read about you, you have said that one of the things you really enjoy doing is making information accessible. And that's exactly what you have done tonight. So thank you very much. And I do have a final question. Are you still playing Dungeons and Dragons?
I wish I was. My group, so yeah, we played for several years. It was all in person, but we've tried to convince people to try the virtual, like using a website. Unfortunately, my group is still back in Vancouver, so I can't play with them in person. I'm still going to try to convince people to give it a shot, but yeah, if I was in Vancouver, absolutely.
Well, thank you again for joining us this evening, and that was very interesting to hear what you're doing, and you know, and have somebody who's, you know, from our part of the world doing this great work. So that's really well done, and yeah, hopefully we can maybe touch base with you, you know, in another couple of years and see what's come up next, and that'd be very interesting. So we've got a little bit of time left tonight. Nathan, you had asked to show a couple of items. Are you still available to do that?
Yeah, sure. Okay. So Michelle, your talk just reminded me of a cartoon that I made a while ago. So this is just basically, for those of you who don't know, and I don't think any of you know actually, because the Sky News edition isn't out yet, but Nerd Anomoly, my cartoon series, is getting a routine section in Sky News. So I'm excited about that. And I figured I'd give you like some sneak peeks about the cartoons that are going to be there. So these are some of my favorites that are the space themed ones that I have made. And Michelle, your talk reminded me of one that I made of the transiting exoplanet survey satellite. It was also just the question that I asked because I wanted to see if this had actually been a problem. I don't know if you guys can see this, but it's basically the team says, thinks they've discovered an Earth-like planet. They analyze the planet, then they do all these readings, think about publishing it. And then when they try to rule out the distance, they find it 600 kilometers away and they realize, oh, they just found Earth.
Yeah, that's definitely is a historic issue, as I said.
And then I also made this one after I observed the lunar X. And for those of you who don't know, the lunar X is it's a landmark on the moon. And when the moon is in its quarter phase, the lighting from the sun makes it appear like an X. So there's a lot of conspiracies about the moon, and I'm just adding one now. I think that the lunar X is the end of a pirate treasure map. And I don't know what the treasure is. It could be like some remnants of the Apollo missions or something. I think that NASA should definitely send an expedition of pirates to investigate this. And then I made this next one while I had a cold, and it was just studying the surface gravity of certain planets. And I think that everyone can relate to this, that when you're sick, the gravitational acceleration of the Earth is definitely higher. Now it doesn't necessarily increase the escape velocity, but it certainly increases the surface gravity, which can be a serious problem. And then this next one is celebrating new horizons as it approaches the edge of the solar system. Now, when Voyager 1 left the solar system, they came up with all these weird definitions of the edge of the solar system. They were like, oh, it's reached the bow shock, it must have left the solar system. It's left the sun's sphere of influence. Oh, now it's left like the heliopause, and it left the solar system about 20 times. And now New Horizons is going through that list too. And I thought that I'd create another definition of the edge of the solar system, which is the M in the diagrams that label the solar system. It's therefore reached the end of the solar system. This one I made when Richard Branson flew into space on his, I think it was the Unity space plane. This is like assuming that somebody used Siri to guide the spaceship, and just the kinds of things that Siri would say. I would really like to see this happen in real life. So if anyone of you goes on Virgin Galactic, I would be honored if you could set up Siri. Then I had this like weird phase where I got into astrology for a short amount of time. So I decided to make a cartoon about a few of the scenarios and the worst case scenario in the end. I really don't know what would happen if a comet conjuncted Jupiter in opposition while Mars conjuncted Saturn and Leo while the moon partially eclipsed the sun with a simultaneous Mercury and Venus transit. But I feel like it would just mean the world's about to end or something. This one, it might take a while to look at, but this is a theory that I have on the Event Horizon Telescope and why their black hole image was so blurry. Now, of course, I mean, we all know that it was because the black hole was 6 milliarc seconds wide in terms of angular size. But I feel like there could have been some other problems too. And this was just one of my theories, that they got really great resolution, except they forgot to set a capture time. And the Event Horizon Telescope wasn't going to take a picture. So they struggle and think of a way that they can capture a picture. They pull out their iPhones and the observation's going to end and their phones are dead. And this one person tries to capture a picture of the capture, but it's blurry and they don't manage to get a good picture in time before it ends. But they don't want to tell us that, of course, because that's embarrassing. And then this one was just, this one was a joke on chocolate bars. And I really hope that when NASA finally sends humans to Mars, they bring these chocolate bars. I would pay the Mars chocolate industry to make a bar like this, because this is just like, this could make NASA so popular if they did this.
Something different.
Anyway, yeah, I'd like to see an Earth bar on Mars, just as we have Mars bars on Earth. This last one was, I don't know, it made my classmates laugh when I brought a telescope to Camp Thunderbird and somebody asked a question. I was basically bringing a telescope to show people the night sky at Camp Thunderbird. And one of my classmates was asking a question about the night sky. And while they were asking a question, they were looking up at the sky like this. So I just turned to them and I said, hey, my eyes are down here, you know. Now I feel like this is like the perfect astronomer pickup line. I don't know if any of you have tried this. I haven't tried it, so I don't know if it works or not. Anyway, these are some of the cartoons that are coming to Sky News soon. So I hope you stay tuned and thank you.
Nathan, you crack me up. Just crack me up. Just fantastic.
Thank you.
That's neat. You're going to be a regular section in there. That's congratulations.
Thank you.
Yeah, congratulations. Those were great.
Thank you.
Randy, did you want to do something else this evening, or did you want to?
When do you want to? I'll do a 5-minute.
Okay.
So oh dear, share that screen first. There we go. Okay, so I'm going to talk about the sun. I don't only talk about the moon. So as you know, we had a rainy, gray day for the Fairfield Fall Fair, and with Sid and Dorothy, and we set up a solar telescope, but there was nothing, no chance to see anything. But one thing that came out of that is I brought this club lovely tool called the Sunspotter home, and it's a fantastic tool. It's so elegant, and I've showed it off to anybody I've had a chance to. And in particular, I guess it was just last weekend, right? It was this really wonderful spot, and I could see it on Saturday and Sunday moving across. And it turned out that it wasn't just any spot. It was this 2882, which is went across, and I could actually see these two little guys. This is a great picture. Who did it? It says on it. Oh, I didn't take the person who took this picture. I think it was done by somebody in Mexico. And it was such a big event that it then led to huge auroras, and there's fantastic pictures all over Canada. But this is from Mount Ptolemy here in Victoria. I don't know who took this picture, but it was put on Facebook by the UVic Observatory. And so nice to see the aurora coming back and getting out of solar minimum. Anyway, that's not really what I want to talk about. What I want to talk about is my choir, the Victoria Philharmonic Choir, actually did a live concert. We were in masks, and the orchestra took the whole bottom floor of the First Met Church, and then only 200 people were in the balcony around. So it wasn't, financially viable, but we were so keen to sing. And what we sang was Haydn's Creation. And in particular, I want to try something new, although if I play sound, will it come through, or do I have to do something special?
If you've got a video with sound, it should play.
Well,
okay, play an audio file. Yeah, you should be able to do that.
Yeah. Anyway, so what I'm going to play for you in Creation, what Haydn did is he kind of illustrated all the stages of the creation, and this is the music of the first sunrise. And this is a picture I took yesterday of a sunset, but imagine it's a sunrise, because I really like this picture. This is off Clover Point. So it's only about a minute long. Tell me if you can't hear it though.
No audio. Nope.
No, did it start?
No, we're not
Oh.
getting that.
Yes, it's going, but you can't hear it.
Well,
Okay.
we could hear it then, but it just started.
Okay, I think what I'm supposed to be doing is saying something in
Randy, reshare, but there's an option when you do your share to include sound.
That's what I thought. Thank you, David, because I thought there was something like that. Share sound. There we go. Try it again. There. That's what I wanted you to hear. I have played that so many times thinking how wonderful to capture in music that just that little glimmer of the sun coming up over the horizon and getting brighter and bigger, and gives me chills. Thank you very much, everybody.
Thanks, Randy.
Thanks, Randy. You could have sung.
Yeah, there we go. We have a couple of items from Edmonton, so maybe I'll show those. Let's see here, and let's see. Oh, come on.
So as a result of that sunspot transit across the face of the sun, it's a coronal hole that generated a whole whack of activity. So this particular image was taken by Eric Klaus's mother, who lives about 5 miles west of Namao, north of Edmonton. And that was done October 9th, and this storm lasted for several days. The next one that you have there is Abdul Anwar, on the 11th at 12:30 in the morning. Again, you can see how amazing and broad across the sky it was. The aurora extended quite a bit south of Edmonton. And then the next bit is, you can run that, Chris.
Yeah, just give me a moment. I should have gotten this started. This just takes a moment to start up. There it is.
So this is Stefan Olsen, and he has an all sky camera in his backyard that he has just put into place. And the little flash you see on the right is somebody's neighbor's motion control light. But that stuff you see in across, that's aurora. And you can see how dynamic it is. This stuff doesn't sit still. So he's just recently put this all sky camera together.
Neat to see the stars moving there too.
Yeah, it is.
That was a good capture.
So it lasted a long time too, because that's over the course of the evening.
Yeah.
And then the last little bit is Anwar again. He's been doing a lot more work with his camera and spending a little more time processing. So this is the Elephant Trunk Nebula, which is up in Cephas. And that's a large image that he had 19.7 hours of data with his 8-inch refractor. And then he decided he would reprocess that. And he reprocessed it with only about 7 hours of data because he had been having trouble with his focuser. And this is a more focused image. And this is just an absolutely stunning image because that's a very faint nebula.
So I'll just go back for a second. So there's all of it.
Yeah.
And a reduced set. I think it turned out very well.
Yeah, he's just getting better and better. He's already a good photographer, but every time you see something from him, his images just get much, much better. And that's it from Edmonton this week.
Great, thank you. And I think David, you wanted to talk about our attempt to reanalyze the sky.
Yes, let me just. So I think if you were around 11 years ago, you probably remember this image of the survey that we did over a couple of months. The SQM readings are mapped to this device here. I think many of us actually have this meter. This one's the regular one, but the one I think most of us have is the one that has a little bit narrower field of view. So I guess the idea is, and thank you for all the people that have already responded. I think we've had over a dozen people that have responded. We don't have as many meters as we do people that would like to participate, but Lauri, we're trying to remedy that, right? I mean, we're going to try to get some additional meters from National.
Yes, the Royal Astronomical Society will loan out some. They're in different places, and different people hold on to them and then loan them out for about 3 months at a time.
Okay.
So they can't be over like a whole long time, but they can be over a 3-month period of time that we can have them, and then we ship them back to the next person on the list. So I think we can get probably at least 3 or 4, probably that way.
Oh, that's excellent.
Yeah.
And actually, I would propose. I think we've talked about this, Lauri, is maybe that the center might buy a few extra meters as well.
And I was talking to a couple of people with the FDAO, and they are like, they would love to be involved, and they think that we should also have one, obviously, up at the center. So we should probably get one as well. So there's a possibility of another couple there for sure.
So I won't get into a lot of the details, but this will occur probably over several months because of the number of meters that we have, and also it does take a while to do this. We're not guaranteed good weather during the moonless week or so that we have defined. Our first opportunity will probably be the first week in November. I'm hoping that we could maybe get organized by then to do the first wave of this. So actually, if you're interested, just let me know. I'm gonna sort of build a list of people that have already said they were interested. We're gonna try to organize a Zoom meeting so I can get into the particulars. There's a fair bit of stuff that we have to do in terms of instructing you how to do this, especially if you didn't participate in the original survey. There's also the other option. I'm trying to see if I can get this here. Get, don't know if I can move this. Here we go. There's also the possibility of using a iOS app as well. This I don't believe this is available on Android, but if you have an iPhone, you can certainly use this. Now, I would not advocate using this to collect the second set of data, but I don't have a problem with us doing this simultaneously. So for those of you who don't have anything, or actually for those of you who are willing to do it, we can actually do iPhone measurements and also use the SQM meters as well. I would like to partition the data sets though. I don't want to muddy the original comparison with the iOS app. But moving forward, if we get this collection of data, the next time we do it, we can use the same method again as well. So yeah, so go ahead.
David, yeah, I have a suggestion that we might consider. If you're going out to take this dark sky meter and you happen to have a 35mm DSLR with a fisheye lens, stick it on the ground, back away from it, take a few exposures at a couple of different exposure values of the sky straight up, because I'd like to see if there are some bright objects around, bright sources around the point where you're taking that image that may influence those dark sky readings as well.
Yeah, that's not a bad idea for those of you with cameras. I mean, we're still kind of developing the protocol. I don't want to alter the original protocol for capturing.
No,
but this is additional information, and that's a great idea, Dave. One thing I've been learning with photometric readings and reporting to the AAVSO is the importance of the metadata. So they actually have a whole section where when you're reporting observations that you actually include conditions. Yeah. So that's a great suggestion. So I'll probably include that. And if you didn't have a camera, we probably would ask you to maybe use a selection of metadata that would describe the conditions, like if there's thin cloud, et cetera, et cetera. Yeah. So anyways, if you haven't reported to me by email that you're interested, there's still time. Just let me know and I'll include you on the Zoom meeting.
Sounds good, Dave.
David, maybe just tell people how long we were out and what it took. I mean, just so people know what it is.
We did it over 2 nights in September, but Sid reminded me that we didn't capture all that data on those 2 nights. So we actually had to go out the next month. And that's why it's September, October, again on a moonless week, and capture the rest of the data. So yeah.
But we were only out for maybe an hour or an hour and a half. Like we went to one site and then do the things, and then we moved to another site and did it. We weren't out for like ages and ages and ages. So
yeah, depending on how many meters we get, I think if we have a lot of volunteers, then we can really divide up the work. So yeah, thank you for all the interest so far. That's excellent.
Great, thank you, David. And Lauri, did you want to make another reminder about the FDAO AGM and Star Park?
Yes. Okay, so the Friends of the DAO are having our annual meeting, which we have to go through on the 30th, which is two Saturdays from last Saturday, and 30th of October. We'll start at 7 o'clock. Go through what we need to for the annual meeting, and then we're going to be having Brenda Matthews from the HAA talk about her work that she's been doing with ALMA, which is the down in Chile, and it's the 10th anniversary. We just actually passed the 10th anniversary of the very first image that ALMA took, and so this is we're into the 10th anniversary, which is amazing to me because I remember it vividly for when it went up. And so she's going to be talking about the debris disks and the planetary disks and how planets are formed, and all the work that she's been doing on some of that work with the telescope, and with a couple of other projects that she's working on, and we're looking forward to having her speak. She gives a great presentation. So what we'll do is, if you are a member of the FDAO, we would love you come along, and we'd like you to register. There's a link. If you're a member, you're going to be given a link to register. If you're not a member, then that's okay. We still like you anyway, and you can come into the whole thing on YouTube. We'll be doing Brenda Matthews' program on YouTube. So anyway, we're getting there. We have been given a permission in kind of a limited way to possibly open for school programs, to have groups come actually up in person. But we have to do still a lot of COVID work, and we have to do a lot of work with the teachers and the program, and what we're going to do up there with the kids, all masked and the whole thing. But we're really happy that we've been given a little bit of some leeway, and we might actually be open to the public and open to have star parties possibly in the spring, is what James said. So we're really looking forward to having that. So anyway, so put the September 30th on your on your calendar and join us then. Thanks, everybody.
Thanks, Lauri. October 30th. Anyways, does anybody else have anything for this evening? If not, I guess that will finish Astro Cafe for October 18th. And I'd like to thank Michelle for joining us again. And thank you for a very, very enjoyable talk. And as I say, well, maybe can get you back in a little while and see what's happened next. This is such a growing field and lots going on. So all the best. And thank you very much again. And does anybody else have any final comments? And I should say thank you to Margie for inviting Michelle.
Yeah, thanks again, everybody, for having me.
Thanks, Michelle. It was great. Yeah.
Okay, well, if that's it for this evening, stay safe, everyone, and we'll talk to you next week.